In this session, we are continuing our exploration of the transformer architecture by focusing on one of the most impactful applications, machine translation. Machine translation is the process of converting text from one language to another while preserving meaning, grammar, and context. Tools like Google Translate and DeepL have revolutionized communication across cultures, enabling seamless multilingual interaction. In this session, we'll explore the fundamentals of machine translation, including its challenges and use cases. We'll dive into hands-on demonstration using pre-trained transformer models like MarianMT for English to French translation. We'll also learn how to fine-tune these models in order to improve translation accuracy for specific domains such as medical or legal texts. Whether you are aiming to understand the basics of machine translation or customize models for your own application, this session will equip you with the foundational knowledge and practical skills. So let's get started.
Hello everyone and welcome back. In this session, we will cover machine translation with transformers. Here is the outline of today's presentation. By the end of this session, you will be able to explain the fundamentals of machine translation and its applications, use pre-trained transformer models, fine-tune transformer models, and evaluate translation quality and identify improvement after fine-tuning. To start with, what's machine translation? Machine translation refers to the process of automatically converting text from one language to another while maintaining its original meaning. Unlike human translation, machine translation relies entirely on computational models in order to understand, interpret, and reproduce content in a different language. The goal of machine translation is not just word-for-word translation, but also the preservation of context, grammar, and fluency to ensure that the translation feels natural. To make machine translation more relatable, let's look at two popular tools, Google Translate and DeepL. Google Translate is perhaps the most widely known machine translation system. It supports translation for over 100 languages and offers features like text, voice, and image translation. DeepL is also known for providing context-aware and fluent translations, especially for European languages. It uses advanced neural network models to improve translation quality. Machine translation is essential in NLP for several reasons, including improved communication, cost savings, increased accessibility, improved efficiency, and language learning. Machine translation has widespread application across various sectors, including cross-border communication, localization, business, education, and government. However, machine translation has a number of key challenges, including handling idiomatic expressions, preserving content and grammar, and adapting to domain-specific terminology. Let's start with the first one, handling idiomatic expressions. This is one of the significant challenges in machine translation. Idioms are phrases where the meaning isn't derived from the literal definition of the words. For example, consider the phrase, "It's raining cats and dogs." A machine translation without proper contextual understanding may interpret it literally, suggesting that animals are falling from the sky. However, the actual meaning is simply that it is raining heavily. Idiomatic expressions vary widely across languages and are deeply rooted in cultural context. Effective translation systems must be trained on diverse and context-rich datasets in order to capture these nuances. Modern transformers, with their attention mechanisms, improve on this by assigning weights to words based on context, but even they require specialized tuning for high-quality idiomatic translations. Another critical challenge in machine translation is preserving context and grammatical structure. Language is inherently ambiguous, and understanding long-range dependencies in sentences is very vital for coherence and accuracy. Consider the example: the doctor told the patient that he will recover soon. Here, the pronoun he creates ambiguity. Does it refer to the doctor or the patient? So without clear context, a translation model may misinterpret the sentence, leading to incorrect or confusing output. Therefore, effective machine translation systems must be able to maintain context across long sequences and also be able to handle grammatical dependencies between words. Transformers tackle this challenge using the self-attention mechanisms. This allows the model to look at every word in the sentence and determine how each word relates to others. This makes modern models far better at understanding complex sentence structures than the earlier approaches. Another challenge in machine translation is adapting to domain-specific terminology. Different fields such as law, medicine, and technology have specialized vocabularies that require precise handling. For example, in legal documents, the word party refers to a person or an entity involved in a lawsuit. However, in everyday conversation, the word party typically means a social event. A general translation model might fail to recognize this difference, leading to inaccurate translations. To overcome this, fine-tuning pre-trained models with domain-specific data is very essential. By training on specialized corpora, we can adapt models to understand context-sensitive meanings and also improve their accuracy for technical content. This is especially valuable in professional and industry-specific applications where precision is critical. Training a translation model from scratch typically uses the pipeline of preparing labeled data, building the network architecture, and training the model with labeled data. This can be implemented using popular frameworks like PyTorch and TensorFlow. Before training a machine translation model, cleaning and pre-processing the data is a crucial step to ensure better model performance. First, we need to clean the text by removing special characters, duplicate entries, and other unwanted symbols that might confuse the model. Next is tokenization, where we split sentences into smaller units such as words or subwords. Techniques like byte pair encoding or sentence space can help create consistent and compact token representations and even reducing out-of-vocabulary issues. Finally, we build a vocabulary that maps each token to a unique index for both the source and the target languages. This step converts text into numerical data that the translation model can process effectively. Let's now walk through the procedure for designing the neural network architecture. We start with a sequence-to-sequence model, which is a standard framework for machine translation tasks. The first part is the encoder. It takes the source text and processes it, turning the sentence into a fixed size representation, which captures the meaning of the entire input sentence. Now, the encoder output alone might not be enough for generating accurate translations, especially when dealing with long sentences. This is why we use the decoder. The decoder generates the target text from the encoded representation. The decoder works step by step, generating one word at a time, and relies on the previous words it generated to help predict the next word. However, long sentences can cause problems when we rely solely on the fixed size context window. To handle this, we introduce the attention mechanism. This allows the decoder to focus on different parts of the input sentence while translating, as opposed to just using the entire face representation. With attention, the model can consider specific words or phrases in the source sentence at each decoding step, and this greatly improves performance for longer or more complex sentences. Now that we have our model architecture in place, it is time to initialize the training process. Firstly, we randomly initialize model parameters. We then set up a loss function and then use an optimizer with the learning rate scheduler. With everything set up, we can now begin training the model. To do this, we use mini batches of data. Instead of feeding the entire dataset into the model at once, we split it into smaller batches, and this helps speed up training and makes it easier to handle large datasets. Each mini batch allows the model to learn from a subset of the data, and after processing all batches, one full training iteration is completed. During training, we closely monitor both the training and validation loss. The training loss tells us how well the model is fitting to the training data, while the validation loss shows how well the model generalizes to unseen data. If the validation loss starts increasing while the training loss decreases, this is a sign of overfitting, meaning the model is simply memorizing the training data instead of learning general patterns. To prevent this, we might use techniques like early stopping or regularization. It is also very important to save checkpoints through the training process. Checkpoints are saved versions of the model at different stages of the training. They allow us to recover the model in case of interruptions and also provide a way to analyze the model's performance at different points in time. Once the model is trained, it is time to evaluate its performance. One of the most common metrics used for evaluating machine translation is the bilingual evaluation understudy, BLEU. It compares the model's output to the reference translations, and it does that by calculating how many n-grams or the sequences of words in the predicted translations match those in the reference translation. A higher BLEU score indicates that the translation is closer to the human reference. However, BLEU alone doesn't give us the full picture, so it is important to also analyze the errors the model makes. For example, the model might struggle with rare words or idiomatic expressions which are often not well represented in the training data. So by looking at where the model fails, we can identify weak points in the learning and then understand where further improvements can be made. For example, like improving vocabulary coverage or fine-tuning on specific types of sentences. Once we are satisfied with the model's performance, the next step is to deploy the model so it can be used for real-time translation. First, we need to package the trained model for inference. This involves saving the model's weights and any necessary configurations in a format that can be easily loaded during deployment. Next, we create APIs or integrate the model into an application in order to make it accessible. APIs allow the models to be able to send text to the model and receive translations in return. This could be done through a simple web interface or embedded within a larger application. The key is to ensure that the model can handle incoming requests efficiently and also deliver translations quickly, making it useful for end users. To assess the quality of our translation models, we rely on several performance metrics like the BLEU I mentioned, that's the bilingual evaluation understudy. Others include the translation edit rate, TER, as well as the human evaluation. Now, the BLEU, bilingual evaluation on the study, compares the n-grams in the model's output to those in the reference translations. Like I mentioned, a higher BLEU score indicates a closer match to the human translation, and then that reflects the accuracy of the model's output. The next metric is the translation edit rate TER, which measures the number of edits required to convert the model's translation into the reference translation. A lower translation edit rate indicates that the model's output is closer to the reference translation with fewer modifications needed. Finally, human evaluation is an important metric where human evaluators assess the quality of translations based on fluency, adequacy, and overall meaning. This is because while automated metrics like the BLEU and the TER are useful, they don't always capture the nuances of translation quality. Therefore, human evaluation is crucial for capturing nuances, idiomatic expressions, and contextual accuracy that automated metrics might miss. Now, fluency tries to check whether the translation is grammatically correct and natural sounding, and then the adequacy checks whether the translation accurately reflects the meaning of the source text. Now, instead of training a model from scratch, which can be resource intensive anyway, we can start with a model that has already learned general language patterns through a process called fine-tuning. Fine-tuning is the process of taking a pre-trained language model and then adapting it to a specific domain or task. Okay? And then as we do that, we continue training the model on that domain-specific data, allowing it to specialize in the target tasks such as medical translations or legal text. This way, the model benefits from both the broad knowledge it has already learned and also the specific insights it gained from the new data. This helps in improving its performance on the task at hand. Why do we fine-tune? Well, fine-tuning allows us to adapt general models to specific domains, significantly improving accuracy. Pre-trained models are great for general tasks, but they may not perform well on specialized topics because they haven't been exposed to domain-specific language. So if we fine-tune on specialized data, the model becomes better equipped to handle specialized vocabularies as well as context-sensitive phrases. This means that the model can understand the nuances of these fields and also provide more accurate and relevant results, making it far more effective for specific tasks. The steps for fine-tuning involves loading a pre-trained model, let's say the MarianMT or other transformer-based architectures if you're doing machine translation. You then prepare a domain-specific data, and then you set your training parameters as usual, where you use a small learning rate to retain general language knowledge, and then adjust the batch size and the epochs in order to balance the performance and training times. Once this is ready, you go ahead and train your model. You use supervised learning to teach the model how to translate or interpret domain-specific tasks. After training, you evaluate and fine-tune your model further. Basically, you measure the translation accuracy using metrics like the BLEU, and then you refine the model with additional iterations as needed. When it comes to fine-tuning language models, there are several tools that make the process more efficient and user-friendly. One powerful tool is the Hugging Face Trainer API. This API simplifies the process of customizing and training models. It handles many of the complex details like setting up the training loop, managing the optimizers, and logging performance metrics. With Hugging Face, We can fine-tune models with minimal code while also having the flexibility to tweak settings for specialized tasks. It is an invaluable resource for quickly adapting pre-trained models to specific domains or applications. The Hugging Face Trainer API is a powerful tool that simplifies the fine-tuning of transformer models. So instead of writing custom training loops from scratch, the Trainer API provides pre-built training loops that handle common tasks and makes the fine-tuning process much easier and faster. It also supports distributed training, allowing us to train models on multiple GPUs for faster results. It also has built-in evaluation and hyperparameter tuning capabilities for optimizing model performance. Some key features of the Trainer API include integrated datasets and tokenizers, which streamline data preparation, customizable training arguments and metrics, so we can tailor the training process to our specific needs, and also a robust login and checkpointing support. This helps track performance and save the model states for recovery or future use. Together, these features make Hugging Face Trainer a go-to choice for fine-tuning transformer models efficiently. Let's now talk about the difference between pre-training and fine-tuning. Pre-training involves training a model on large general datasets like Wikipedia or Common Crawl, and these massive datasets help the model to learn broad language patterns, grammar, and general knowledge. Pre-training gives the model a strong foundation by exposing it to a wide range of text from different domains. Fine-tuning, on the other hand, focuses on smaller domain-specific datasets. Once the model has learned general language features from pre-training, we can specialize it by further training it on targeted data, let's say medical text or legal documents. This process adapts the model to handle the specific vocabulary, phrases, and context of the new domain and helps in improving its performance on specialized tasks. Let's now talk about the MarianMT model, which is a multilingual neural machine translation model developed by the Helsinki NLP group at the University of Helsinki. It is part of the broader MarianMT project, which is an open source initiative for machine translation. MarianMT is known for being efficient and highly optimized for both training and inference, and this makes it to be an ideal choice for large-scale translation tasks. The MarianMT model supports multiple language pairs and provides robust translation capabilities. It's also widely used in research as well as real-world applications for multilingual text processing. Let's now look at the key features of the MarianMT pre-trained model. The MarianMT model is specifically designed for multilingual translation, which means that a single model can support many language pairs. MarianMT is built on the transformer architecture. The transformer models uses self-attention mechanisms to process input data in parallel. This makes it more efficient and faster than older sequence-based models like RNNs and LSTMs. MarianMT models are pre-trained on large multilingual datasets and are ready to be used for translation tasks without needing further training. You can load them directly from the Hugging Face Model Hub. One of the highlights of the MarianMT is its ability to handle many-to-many translations, meaning that it can translate between multiple languages and can also be trained with many different pairs of source and target languages. MarianMT is well regarded for its high translation quality and efficiency. It has shown competitive results when compared to other state-of-the-art translation models such as Google Translate and DeepL for many language pairs. Although pre-trained models are available, You can also fine-tune MarianMT on a specific dataset or domain. You can do that in order to adapt it to a specialized translation task such as legal text, medical text, etc. MarianMT supports over 100 languages, and it is pre-trained models are available for hundreds of language pairs. Let's look at some real-world case studies where machine translation models are making a significant impact. One powerful application of machine translation is in medical translation. For example, fine-tuning a MarianMT model on clinical trial data has been shown to significantly improve translation accuracy for medical terminology. This is critical because general translation models often struggle with the precise and specialized language used in medicine. A fine-tuned model can handle complex terms and context better. Another impactful use of machine translation is in legal document processing. By adapting a general translation model to legal text, we can achieve more precise interpretations of contracts, case law, and other legal documents. Legal language is highly technical, having unique structures and terminology that require specialized training to translate accurately. For instance, imagine the task of summarizing multilanguage legal proceedings. And achieve more precise models can help lawyers and legal professionals quickly understand the content of documents from different jurisdictions, saving time and ensuring accurate cross-language legal communication. Technical documentation is another area where machine translation proves invaluable. Translating user manuals or software guides demands a deep understanding of domain-specific language and terminology. Generic translation models may miss the mark when handling precise technical phrases, formatting, or symbols, which can lead to confusing or inaccurate translations. A great example is localizing programming tutorials for non-English speaking audiences. By fine-tuning a model on technical content, we ensure that complex programming concepts, code syntax, and instructions are translated clearly, helping more people to access and learn from these resources in their native languages. Fine-tuning can be very effective, but it also comes with a few challenges that need to be managed. One common issue is overfitting, where the model becomes too focused on memorizing the training data rather than learning to generalize. This means it might perform well on the training set, but struggle with unseen data. To avoid this, we need to monitor performance and use techniques like regularization or data augmentation. Another challenge is the scarcity of high-quality domain-specific datasets. For many specialized fields, such as medical or legal domains, the available data might be limited or hard to collect. This makes fine-tuning more difficult, and we may need to use synthetic data or adapt data from other sources. Lastly, catastrophic forgetting occurs when the model loses its ability to handle general language tasks because it becomes too focused on the domain-specific data. To mitigate this, it's important to use small learning rates and to carefully balance domain-specific and general tasks during fine-tuning. Let's go over some best practices for fine-tuning to ensure your model performs well. When you have limited data, generating synthetic examples through data augmentation can help increase the diversity of your training set. This reduces the risk of overfitting and improves the model's ability to generalize. Also, a small learning rate during fine-tuning is important because It helps minimize the risk of catastrophic forgetting, where the model forgets what it learned during pre-training. Small steps allows the model to adapt to new data without losing its foundational knowledge. Regularly evaluating the model's performance on both domain-specific tasks as well as general tasks is also important. This ensures that fine-tuning doesn't compromise the model's ability to handle general language while also improving performance on specialized tasks. To avoid overfitting, it's a good idea to use early stopping, which halts training when the validation performance stops improving. This helps prevent the model from overtraining on the data, ensuring it generalizes well to unseen examples. Some tips for effective fine-tuning include pre-processing data thoroughly to ensure quality, leveraging pre-trained models best suited for your domain, and experimenting with hyperparameters for optimal performance. Time for practical walkthrough in Python.
So in this particular lab, we're going to start with how to train a transformer model for machine translation from scratch. We are actually going to be using this particular dataset. It's a corpus for English to French translation. So for every English word go, there is a corresponding French translation. For example, here go, we have va, then we have run. So for every English word, there is a corresponding French translation. And let's see the end of the data. It's about 229,800 and something. So it's a very huge data. So the first thing we do is, of course, is to start by importing our libraries. We import all the necessary libraries. Then we're importing Torch, where we're going to use datasets, data loader, random split, part sequence, etc. Of course, we're going to be developing a transformer model, so we have to import the transformer library, okay, amongst others. This BLEU is used for computing the BLEU performance. Remember, we've discussed that this is the key metric used in evaluating the performance of a translation model. So let's run this. Yeah, if you run this, close this, and then the next is to prepare the data. So we're importing this particular CSV file from the same directory. But since I'm just going to training these models can take really huge amount of time, and since I simply want to illustrate, so I don't want to use the entire data, so I'm taking 1% of the data. So 1% of that data would be like 0.01% of the entire sample of the data, and that's why I'm creating this data frame to simply sample 1% of the entire data. So 1% of 228,000 should be around numbers that we can handle, okay? And then here, this is where we are taking the English column and the French column. If you look at the data set, there is a column for English and there's a column for French. So we want to use this as our this and this as our sequences. So that's what we're doing here. We can just run this now, okay? Then this is where we set our vocabulary. So this is where we are tokenizing, and for example here, we're writing a simple for loop, and then this tokenized function splits the sentences into words for further processing, okay? So this is the entire code that does that. You can just run it, okay? This basically setting our tokenizer and initializing our vocabulary to build from that particular sentences that we have. So the next is the loading of the data sets, okay? So we load the data set. So this handles the entirety of this code, handles the pairing of the source target sentence and then encode them into tensors. And of course, we want to ensure that we have our split. Okay, so where is it? So here, this is where we have our split data, because we want to train our model on the train split and then evaluate on the validation split. So we divide the data set into training. As you can see, 80% is for training, and then the remaining percentage would be for the testing. So this is actually where we are setting and loading our data set. Let's run this and see. Okay. Setting the model definition. It's a transformer model. So we have this particular class that implements the encoder decoder structure with multi-head attention, and then we also have the output layers, okay, that maps the transformers to the target vocabulary, and then we also have the embeddings here. Okay, we have some embedding layers here from neural network embeddings that convert the word indices into dense vectors, etc. So maybe we can just run this code here. As you can see, there's positional encoding here that's added. So the positional encoding is added here to preserve word orders amongst many others. So essentially, this is where the model definition is set. If you recall from the class, we said you prepare your data, you build your model, and then you train. Okay. So we can now run this. We are running on a CPU just for illustration. So we run this. And then at this point, we train and evaluate our model. So this is where we set the optimizer, okay? This is the criterion. Remember, we said we are going to use cross entropy loss. That's a typical loss function that we use in sequence-to-sequence model, especially for translation, okay? And then this is the function for computing the accuracy, okay? And then we're running this for 10 epochs, just for illustration. And then this is where we evaluate the model evaluations, okay? And then if you run this, the model should be ready for training now. So like I said, I'm just using a small fraction of the data set. So that's why it's even practical for us to train the model. But in reality, training this type of models usually takes some huge amount of time. So it's still training the 8th epoch. Okay, it has finished training. Although this is not so prominent when you're doing translation models, but just for completeness sake, I said, let me add the learning curves just for us to see the progression as the model is being trained from one particular epoch to another. That's because translation task is really a difficult task. And if you don't train on huge amount of data, you might still get a very bad value of the BLEU. So, but just for us to see the progression as the model is trained from one epoch to another, I just said let's plot the curves, the loss and the accuracy curves, and then this is the code that does that. Okay. So just for a few epochs, just to see that, yeah, as we progress from first epoch to the last epoch, the loss is getting smaller, and then the accuracy is also improving. And then this is where the BLEU score evaluation is computed. Remember, I said running this, the code that computes the BLEU score, like we said, we are simply training a very small amount of data. So even if we run this, the BLEU score is going to be very small. But at your leisure time, you can raise the value. You can raise the value so that you can use the entire data sets, and then you see how the value can improve. So really training from scratch requires huge amount of data, and that translates to huge computing resource and then more training time amongst others. So you can see that the BLEU score is 0.00, and this is expected because we are working on a very small amount of data, and then the algorithm has not learned so much to be able to match the n-grams as it is in the original translation. It is at this juncture that we would now look at how pre-trained models work for translation tasks. For the pre-training, we are simply loading the pre-trained model, and in this case, we are going to be using the MarianMT model and tokenizer for English to French. The model name is Helsinki NLP / Opus MTN FR. So this is what corresponds to the pre-trained MarianMT model for English to French translation. We also have here the Marian tokenizer here is the one that's responsible for converting text into token IDs that the model can be able to process. The MarianMT model here is the one that performs the translation based on the tokenized input. So both the tokenizer and the models are loaded using the from pre-trained method. Okay, so we are all using this from pre-trained method to load both the tokenizer and the model. Okay, and then this is where we set some few sentences. Okay, we have English sentences. The first one is how are you? The second one is what's your name? The third one is I love programming. Transformers are powerful models. Please translate this sentence. These are all sentences, isn't it? And then here we are using a simple for loop that hovers over the English sentence. It hovers over this list. This is a list. So this for loop hovers over this particular sentences, and for each input, we're getting we're feeding in the tokenizer function to that particular variable that has been selected from that particular list. So it carries this as the first instance, this as the second, this as the third, till the last. So in every instance, the generate function here for each and every sentence, the generate here is the function that generates the token IDs for the translated text, and then we also decode. Of course, you know, the transformer architecture is based on the encoder decode architecture. So the decoder, this tokenizer.decode function is the one that converts the generated token IDs back into a readable French string. Okay, and then we can just run the code. Here we are just printing the translations, and then if we do that and we run the code, we'll see that it's going to give us the desired output. You know, loading the pre-trained models can take quite some time, so it has finished. So you can see that for the first sentence, it has translated it, hello, how are you, to bonjour, blah, blah, blah. And for some of you that speak French, you see that the translation is really in par with state-of-the-art models. For the second one, this is the result. For the third one, etc. So basically, this is how we use the MarianMT model to perform English to French translation. And in the next tutorial, we're going to show how to now fine-tune a MarianMT model for a specific domain task, okay? So in this particular lab, we are going to fine-tune a pre-trained English to French translation model using the Hugging Face transformer model. In the class, we have clarified the difference between pre-training and fine-tuning. In the previous lab, we only used the MarianMT model for our task. So we simply adopted it as our model. But in this example, we are fine-tuning. It means we are localizing, we are trying to adapt the MarianMT model for our own localized data sets. And let me take you, let's take us through to what's happening here. The first thing, we import the necessary modules as usual. We import both the tokenizer and the model itself, the class that imports the model. We are going to specify the model later, okay? And then here we're just suppressing errors, okay? And then this is where we loaded the data that we are going to be adapting the MarianMT model on. Is that okay? Okay, and of course, because we are just illustrating, we don't want to use the entirety of the data. So we simply use, let's say, 1% of that particular data. So let me just run this code now. So if I run it now, I import the data, and then this is where I prepare the training and the evaluation data. Okay, as usual, we are making it 80% for training, and then the remaining 20% for testing. Okay, so this is where we have the eval data, okay, and then the training data, isn't it? This is the 80% for training 80%, testing 20%. And then this is where we create a data set object for Hugging Face. So whatever we have in the columns for both the English and the French columns in the data set, we are converting them into this Hugging Face data set dictionary. Okay, and then we can run this also and see. And then at this point, this is where we load the translation model. Remember in the class, we said there are several models to this type of, there are several MarianMT models. But for this example, we want to use the Helsinki NLP Opus MTENFR. And this model corresponds to the Hugging Face pre-trained model for converting from English to French. So of course, we are just running on a CPU, so we don't want to complicate things. So we can just run this, okay? So we have to wait for it to finish loading. Okay, so it has finished, okay? And then the next thing is to tokenize this, telling us some details about the model that we have loaded, okay? So these are some details you can get about it. And then this is the function that does the tokenization, isn't it? We all know what tokenization is all about, isn't it? We want to ensure that the textual data is tokenized appropriately, okay? And in this case, we are using that tokenizer function that we have already imported. So we run this, and then this is where we configure the trading settings, okay? So that's where we set all our training configurations, the number of epochs, amongst others. For this, I'm simply setting the number of epochs to be 1 because fine-tuning a pre-trained model can also be computationally intensive, especially if you are using the entirety of the datasets. So that's why I just want to use 1 epoch for illustration. And at this point, that's where we evaluated the performance of the model, okay? We're seeing the accuracy, the precision, the recall, as well, and most importantly is the BLEU score, because this is the most important performance metric when you're doing machine translation. Even though this can be seen as some sort of supervised machine learning problem for classification, but since it is sequence to sequence, so that's why with this more reliable. And then this where we initialize our trainer, okay? This where the sequence to sequence model is initialized, and then maybe we run, where did we run this? Let's run the configuration, okay, and then we define the evaluation metrics, and then this is where we initialize the trainer, okay. So this is where the magic is happening, okay? This is where the training is happening. So we are using the pre-trained model as a starting point and then continuing on training using our own traditional pipeline on our domain-specific data. So this can really take some time. So you notice that maybe I will be pausing the recording until it reaches the desired position I want it. Then we'll continue so that the video will not be more than 1 hour as usual. Okay. So we are still in the first epoch. As you can see, this is the worst. We are in the 0.04th epoch, isn't it? So in one epoch, we've not even reached 1/10 of the first epoch. So it will continue doing this until the first epoch is concluded. We have to be a bit patient. So I think it's progressing. So it's still at 0.7. So if you look at it carefully, because this is actually the heart of the pre-training process, isn't it? Okay, so we have this sequence to sequence trainer. Okay, so it's this line that creates an instance of the sequence to sequence trainer class, and it passes the following as arguments. Number one is the model that we've trained, the pre-trained or custom sequence model that we have already trained. That's the Helsinki, where is it? The Helsinki ENTR, isn't it? Yeah. This is the model that we have already named, and of course from here we are calling from pre-trained based on this model. Okay, and this argument train args is just telling us that the trained dataset is an object that contains various training arguments like the learning rate, the number of epochs, amongst others. And then the training dataset is tokenized to, we're tokenizing the train here, we're also tokenizing the evaluation. So we are tokenizing both the training and the evaluation. So once this have been set, we simply train the model on that particular trainer. We train this particular configuration, and then this is what is happening. And then as you can see, since it's one epoch, so for every batch we are seeing that the kind of losses we are getting. Okay, as you can see, the loss as we progress from one batch to the next is really reducing. Is that okay? I think it's reducing. Yeah, and then most importantly, the learning rate is also reducing because we're using learning rate scheduler. Okay, and then this is where we have the various epochs. So I think it's almost done now. So the training process has finished. So I think we can now evaluate the model. Okay, and of course, if you are evaluating, we are evaluating on the testing data. So let's evaluate and see. Okay. This can take quite some time also, but let's just be patient. So it has finished. So since our model is ready, I think we can now take time to now generate some sample translations. But before that, remember that when we trained our model from scratch, we got our BLEU value to be about 0, isn't it? But look at it now. By simply fine-tuning using one epoch, we are getting a BLEU value of close to 0.56, because the value is either between 0 to 1, or depending on the implementation, it can be between 1 to 100. So you can see that for just one epoch, we are having a BLEU value of about 0.56, which I think is not bad. You can imagine if we are using maybe 10 epochs and we're even increasing the size of the training data, because here we only train this on 1% of the data. So I think now we can now use this to now see what the output would be. So I have a simple sentence here. Hello, how are you? I love machine learning. let's go to the market. Let's see what the fine-tuned model is going to return as output. Yeah, so we have hello, how are you? The translation is bonjour, comment, allez vous. Yeah, this, I don't speak French, but I think this is the correct correct translation for hello, how are you? Even if you check it on Google Translate or any other translation machine. I also have here, I love machine learning. Yeah, and I think also the translation for this, even if you check Google Translate, is going to be something like this. So you can see the power of fine-tuning a pre-trained model on your own localized task, isn't it? So, and I want to believe you, all of you have an appreciation of how to train uh, transformer models for machine translation from scratch, and how to use pre-trained models, and how to also fine-tune the pre-trained models for our own local task.
Well done on completing today's class. Here are the key takeaways. As always, here is an assignment for you where you are to upload to the learning portal. Here are some resources for further reading. In our next class, we shall look at bidirectional encoder representations from transformers, BAT. Thank you very much for your attention.
Well done on completing today's class. Let's quickly recap the key points we've covered. We began by exploring the fundamentals of machine translation, discussing real-world tools like Google Translate and DeepL, along with the challenges of preserving context, idioms, and domain-specific accuracy. We had a hands-on session using pre-trained transformer models like MarianMT for English to French translation, showcasing how easy it is to leverage these powerful tools. Finally, we delved into fine-tuning transformer models, learning how to adapt them to specialized tasks such as improving translation accuracy for specific domains. A memorable takeaway from today's session is that transformers make machine translation not only accessible but also customizable for your specific needs. This is something you can start applying right away. To ensure you're engaged and practicing, I have prepared an assignment for you. Upload your code implementation, results, and a brief report of your findings to the Learning Portal. For support, you can reach out to the teaching assistant or engage with peers via Google Classroom. Thank you for your active participation in today's session. I encourage you to explore further applications of transformers in multilingual tasks. Keep practicing and experimenting, and I look forward to seeing your work in the next session. See you soon.